This problem describes a two-step process. Since the piston can move freely during the first part of the process, the gas mixture will expand as the reaction occurs until the piston hits that set of stop bars. During this step, work is therefore being done by the system against a constant boundary pressure, and in our energy balance that is equal to the change in internal energy during this first part of the process. During the second part of the process, the pressure of the gas mixture will increase with the increase in the number of moles, since the change in volume for that part of the process is zero. There is therefore no work, and since the process is adiabatic, the change in internal energy for the second part of the process must be equal to zero. By combining the two terms for the change in internal energy, we can prove that the overall change in internal energy for that process is equal to the work delivered in step 1. Since we have a mixture of ideal gases, we can express the pressure at the end in terms of number of moles, temperature, and volume. We therefore have 4 unknowns and we need 4 equations to solve the system. The given mole fraction for component A gives us our first equation, which allows us to use our stoichiometric table to solve epsilon as 0.25. This allows us to solve the first unknown in our equation. Careful with the units if you want to work with kilopascals, moles divided by 1000 to get it to kilomoles. The mole fractions are now known from our stoichiometric table, and we can express our equilibrium constant in terms of our unknown pressure. If we want it in kilopascals, standard state must also be given in kilopascals. We can now substitute the resultant expression, which is in terms of the unknown pressure at the end, into Van 't Hoff's equation, which gives us an extra equation in terms of 2 unknowns, temperature at the end and pressure at the end. Another equation can be set up by considering our overall energy balance. We can break the internal energy down to the part where the reaction takes place multiplied by the moles reaction, and that is of course where we have information at 298, plus the products that then needs to be heated up to that final temperature at the end. We can write the work in terms of the unknown volume at the end, and using the ideal gas law, which is of course our fourth and final equation, we can write the work also in terms of just the pressure and the temperature at the end. We have now simplified it to 2 equations with 2 unknowns that we can solve simultaneously. In the absence of Python, we can once again use a trial and error procedure by first guessing a value for the temperature and solving the pressure from equation 1. Since we can now calculate K, we can calculate a new temperature at the end from equation 2. Now the loop can be repeated until convergence.